Okay, so we're going to conclude our unit on conservation laws by looking at power. By the end of this, you should understand the definition of power so that you can calculate the power required to maintain the motion of an object with a constant acceleration, and to calculate the work performed by a force that supplies constant power, or the average power supplied by a force that performs a specified amount of work. So here we go. In many situations, it's useful to know how quickly energy is transferred or transformed. For example, when passing a truck, your car needs to transform a certain amount of chemical energy into kinetic energy. That makes a big difference whether your engine can do this in 20 seconds or 60 seconds. So this question, how quickly, implies that we are talking about a rate. The rate at which work is done is called power. So here is our power equation. It's work over time, the rate at which work is done. From looking at this equation, we can see what the units for power would be. Since work is measured in joules, time measured in seconds, the units of power would be joules per second. Now, because we like to honor those scientists who've made significant discoveries, we often name the concepts they discover after them. We do this in a variety of ways, but one way is to give them their own unit. James Watt became such a fellow when he perfected the steam engine. So we name the unit for power after him and call it a watt. Now, Watt himself developed his own unit for power, we still use it today. It's called the horsepower, or HP. Horsepower is used for cars and large motors, while watts is used for smaller appliances that run off electricity, such as toasters, refrigerators, waffle irons, coffee makers, heaters, whatever. The conversion factor for horsepower to watts is 1 horsepower is equal to 746 watts. In physics, we typically use watts as our unit of power. Now, because power is the rate at which work is done, and work is the mechanical transfer of energy, we can also define power as the rate of change of energy. If we're dealing with mechanical energy, such as climbing a mountain or driving a car, we can look at the change in gravitational potential energy or kinetic energy or whatever energy we're dealing with and divide that energy change by the time interval over which it changes to get the power. For example, if it takes, say, 5 seconds for a 50-kilogram person to climb a 5-meter tall staircase, we can take that change in gravitational potential energy divided by the time interval to see that they generate 490 watts of power as they climb the stair. We know this power will be measured in watts because energy is measured in joules and time is measured in seconds, and the equation shows joules per second, which we call watts. So that's 2 ways that we look at power: the work over time, change in energy over time. There's another way that we can define power, and we need to look at that as well. So power is the rate at which work is done, right? And we've been able to define work as the change in energy. So this means that power is the rate of change of energy. Well, we've also defined work as FD cosine theta, right? So we can also define power in terms of the force and displacement. When we do, we get FD cosine theta, which is our expression for work over time. Well, when we look at this equation, then what is one thing that we notice right away about that equation? Well, we notice that this quantity right here, this d over t, is really just velocity. It's displacement over time. So this becomes power is equal to the force times the velocity times a cosine theta. Now the angle in this equation refers to the angle between the force and the velocity. Now each of these 3 ways to look at power gives us different ways that we can not only solve problems, but also ask problems. We can be asked about specific changes in energy over time and figure out the power. We can be given information about work done over time and figure out the power. We can be given information about forces and velocities and figure out the power. One of the main points here, though, is that the faster work is done, the greater the power that was developed. Work doesn't care about time. It only cares about a force acting, however slowly or quickly, to bring about the movement of an object. A powerful engine is able to do work faster than a less powerful engine. It may well do the same amount of work, but the more powerful engine will do the work much more quickly. So let's take a look at some examples. So for our first example, we've got the power to pass a truck. And this example is in your reading packet. We're going to look at two other examples that are not in your reading packet. So you should just prepare yourself to put those down in your notes somewhere. So you're behind a truck in this example, in your 1,500 kilogram car, traveling at 27 meters per second, which is about 60 miles an hour. You want to pass the truck, so you speed up to 34 meters per second, which is about 75 miles per hour, and you do that in 6 seconds. We want to know the power required to do this. So whenever we're faced with a power question, what we want to ask ourselves is, are we dealing with a change of energy? Are we dealing with, can we throw work involved in this? Or are we looking at the application of forces? With this particular problem, it's going to be easiest if we solve this from an energy standpoint, so that there's changing energy over time. So we have to ask ourselves, what type of energy is it that's changing here? And since we're going from one speed to another speed, we're going to recognize right away that we're dealing with kinetic energy. So we're looking for the change in kinetic energy over time, which will be our final kinetic energy minus our initial kinetic energy over our time interval. So remembering that our expression for kinetic energy is 1/2 mv squared, we end up with this, where we have our final kinetic energy minus our initial kinetic energy over our time interval, and we can plug in our values, and here's what we end up with. We end up with 53,375 watts. Now, often in an answer like this, we're going to convert it to kilowatts just to make it easy, so we end up with about 53 kilowatts, which is about 71 horsepower. Now, keep in mind, this power is in addition to the power needed to overcome drag and friction to cruise us along at the 60 miles an hour. So the total power required from the engine will be even greater than this, which shows that we use a really large amount of energy to perform simple driving maneuvers such as this. So this amount of energy is enough to lift an 80 kilogram person 410 meters in the air, which is the height of a tall skyscraper, and 53 kilowatts would do that, would get them there in only 6 seconds. Let's take a look at another example. So here we've got a 60 kilogram jogger running up a flight of stairs in 4 seconds. The vertical height of the stairs, 4.5 meters. What's the jogger's power output and how much energy did that require? So now here in this problem, the power is change in energy over time. And this person is going up a flight of stairs, so they're changing their gravitational potential energy. So in this case, our power is going to be equal to our change in gravitational potential energy, which starts at the bottom here at 0 and goes to something above 0 at the top of the stairs. So we end up with mgh over time. And we end up generating 661.5 watts of power to get up this staircase. Now, since there's 746 watts in 1 horsepower, the jogger's doing work at a rate of just under 1 horsepower. A person can't do that rate of work for very long. And since we're changing our gravitational potential energy, the energy that's required to do this is just equal to that change in gravitational potential energy, which is about 2,646 joules. We'll be doing a lab after this video dealing with our own personal power output as we climb some stairs. We'll also see some other examples of power in our practice time in class. We'll see you then.